Okay, so we're going to do another calculation question. And most of the calculation questions are mechanicsy rather than materialsy. So this is one where it's to do with momentum. We're going to write the magic stuff down again. So we're going to read it. We're going to read it again. Then we're going to draw it. Then we're going to put everything we know about it. And then we're going to sort of have a look at a process that takes us from what we know, known, to the unknown. Okay, so a game is played where each player must use a mallet to hit a disc across a table into the opponent's goal. One player accidentally lets go of a mallet. The mallet travels at a speed of 1.6 meters per second and collides with the stationary disc. Okay. After the collision, the mallet continues in the same direction at a lower speed of 0.3 meters per second. The disc moves in the same direction as the mallet with a velocity v as shown. Before collision, after collision. Calculate a value for v. Assume that frictional forces are negligible. They give you the mass of the disc and the mass of the mallet. Okay, so let's make sure we got this. A game is played where each player must use a mallet to hit a disc across a table. Okay, right. One player accidentally lets go of this mallet, so this mallet is on its way at 1.6 meters per second, and it collides with a stationary disc, hits this one. So this is before the collision, this is after. After the collision, the mallet continues in the same direction at a lower speed of 0.3 meters per second, lower than the 1.6 meters per second, and the disc moves in the same direction as the mallet with a velocity v as shown. Now, looking at this quickly, we would expect, as the mass of the mallet is big compared to the mass of the disc, we'd expect the speed of this dude to be rather large. So we think it's going to move, which kind of makes sense, but that's just as a thing. Now, we're going to draw it out. Well, we'll draw and put, it's actually drawn already, but let's put some information here. So this disc has got v equals 0 meters per second. This has got a mass of the mallet, I'll just call it, which we know, and we know the mass of the disc, md. And then this is the mass of the mallet, and we know this velocity. Okay, velocity of the mallet, we know this. And the mass of the disc, we know again. So this is going to be quite straightforward. The principle in this, going from the known to the unknown, the principle of this is that the momentum before is equal to the momentum afterwards. And what is momentum? Momentum is equal to mass times velocity. So basically the sum of the mass times the velocities here must be equal to the sum of the mass and velocities there. Okay, so what is the before momentum? Before we've got, well, let's work out. We've got the momentum of the mallet, which is the mass of the mallet times the velocity of the mallet. And we don't have anything else because this is 0. And after, I'm going to do it in one line because I think it's relatively easy. After we've got the, let's have a different colour. We've got the mass of the mallet times the new velocity of the mallet, which we know. And we're going to add to this the mass of the disc times the velocity of the disc. Velocity of the disc is what they're calling v. Okay, we know these guys got to be equal. Simple. So I'm going to rearrange it first before I put any numbers in, because usually that's the best thing to do so you don't get in a mess. So I'm going to rearrange this, and I'm going to say, first of all, I'm going to move this to the other side, and I'm going to say that the mass of the mallet times the velocity of the mallet initially minus the blue velocity of the mallet is equal to the mass of the disk times the velocity of the disk. So I moved that and I took m outside. And then I'm going to get rid of this guy, move that over to the other side, and so I'll have the mass of the mallet divided by the mass of the disk times the initial velocity of the mallet minus the new velocity of the mallet. I'm just going to keep that in blue so it's kind of obvious that it's different. I don't want lots of labels. I could say the velocity first, before, and all that sort of stuff, but it'd be too much, is equal to the velocity of the disk, which is equal to this thing, which is equal to v. That's what they're calling it. So let's slap in the numbers. So you've actually got the mass of the disk mass of the mallet, 0.17 kilograms, divided by the mass of the disk, 0.035 kilograms. And the velocity of the mallet is 1.6 meters per second, minus the new velocity of the mallet is 0.3 meters per second. That's it. Okay, let's slap in our calculator and work this out. So 0.17 kilograms divided by 0.035 is equal to 4.81 times, we can just quickly do that, times 1.3, we can see that, times 1.3 meters per second is equal to 6.31 meters per second. V equals 6.3 meters per second. There you go. Nice one. Right, to reach the goal, the disk must move up a ramp which is at an angle of 30 degrees to the horizontal. Let's have a look at this. This is interesting. The velocity of the disk at the bottom of the ramp is 5 meters per second. The disk moves up the ramp and work is done by the disk against the frictional force. This is all getting a bit confusing. The disk moves a distance of 6.5 centimeters up the ramp before moving back down. Determine the frictional force acting on the disk. Okay, so again we're going to read it twice. To reach the goal, up here, the disk must move up a ramp which is an angle of 30 degrees to the horizontal. Okay, fine. The velocity of the disk at the bottom of the ramp is 5 meters per second. The disk moves up the ramp and work is done by the disk against the frictional force. The disk moves a distance of 6.5 centimeters up the ramp before moving back down. Determine the frictional force. This is where drawing it really wins. So what we've got is we've got it going to about this position, and it's moved up a certain distance here, and it's also moved a certain distance along the slope. I'm going to relabel this one actually the height, because you'll see why in a minute. But it's moved up a vertical distance and it's moved along the slope a certain distance here. And there's a very easy way to do this question and a very complicated way to do this question. Now, the easy way is always, if you can, use energy. If you don't have a time component, and see then nowhere they're asking for time, you can always look to use energy. And the good thing about energy, it's kind of similar to momentum in its conservation of energy. Conservation of momentum says the momentum before and after are equal. And so we're saying the energy before and after are equal. So what's the before energy? Before, we've got, well, the velocity of the disk at the bottom of the ramp. So at the bottom of the ramp, we're going to say that it's got kinetic energy and it's got potential energy of 0, because we're going to take this layer as kind of the base, 0 PE, gravitational potential energy. we could say GP equals 0 here. The kinetic energy is a half mv squared, but we know the mass and we know the velocity. So that's good, we've got that. Now, so initially we only have a half mv squared. Now after, when it's in this position, final position, well, the highest position if you like, final position, what have we got? Well, the reason it stops and slows down is because, well, not the reason is, but at that point you know that the kinetic energy equals 0, because as it turns around it's like reaching its maximum height, its velocity is 0. So its potential energy is equal to mgh, whatever this distance is, height. But we know what that is because we know d, and d equals 6.5 centimeters. So we can work out, can't we, that if this is the opposite length, so if you want to use sine, you can say that sine 30 degrees equals opposite over hypotenuse equals h over d. Rearranging it, we can say that h is equal to d sine theta, 30 degrees, which is equal to 6.5 centimeters. Sine 30 degrees, we probably should know this is a half. So equals 3.25 centimeters. So we know this height. So we know the potential energy at the end. But so let's just say after we've got, let's go for this mgh, which we know. Now they're not going to be equal because conservation of energy says that the total energy is always the same. Now what's happened is that we've lost energy used up against friction, lost energy working against friction. Now what we should know about work done by a force against friction, against anything, is equal to, the work done is equal to the force times distance. Now we know the distance because it's the distance up the slope. And so the frictional force is equal to the, well, let's leave it as the work done, or the work done, the lost energy is equal to the force, frictional force times the distance. So what you have is this situation. The energy that initially was kinetic energy has converted into potential energy, but some of it has been lost working against friction. So what you end up with is this. So the starting energy, half mv squared, does two things. Is equal to the potential energy it ends up with and the work done against friction. That had to come from somewhere. It came from the kinetic energy to start with. So we can rearrange this and say that the frictional force times the distance up the slope is equal to half mv squared minus mgh. And we can say therefore that the frictional force is equal to half, I'm going to take m outside. I won't take the half outside actually. Let's take m outside the brackets. M, and then I've got v squared over 2 minus gh. And all of this divided by d. So I'm now going to slap my numbers in and just make sure we've got everything. I think we've got everything. So the mass of, this is the mass of the disc, which is 0.035 kilograms. I'm going to put the numbers in anyway. So 0.035 kilograms divided by the distance up the slope, which is 6.5 centimetres, so 0.065 metres. And then I've got the velocity squared over 2. Velocity squared, so the velocity is 5 meters per second. 5 meters per second. 5 meters per second squared divided by 2 minus 9.81 times the height, which is 3.25 centimeters, 0.0325 meters. All this lot. It's a bit messy when you put the numbers in, but it's always worth it. It's then much easier. 0.035 divided by 0.065 equals 0.5 times, I'm going to open my brackets, 25 divided by 2, which is 12.5, minus 9.81 times 0.0325 equals, gives us an answer of about 6.56, which is about 6.6 newtons. Okay, and we have plenty of space down here to do it, but I always like working on the diagram so I can see what I'm doing. So in principle, how we do this, we use energy, and we say that the starting energy does two things, and it goes into work done against friction, and it also raises the thing up the slope plus potential energy gained. So in this one, half mv squared is equal to the frictional forces, if you like, times the distance it moves, and then plus the potential energy, gravitational potential energy, mgh. And just to give you a nice diagram, what we've got here, we've got the thing moving up the slope to a certain distance there, a certain height there, 30 degrees, which we can find out, etc., etc. Start. There you go. So that's that one. 6 marks for that. Good question.